Good morning, students. So the last session itself, Unit 5 is over. Okay, so I have already told about Unit 5. The problematic part, which is very low comparative with remaining units, but PCP problem, post correspondence problem, and modified post correspondence problem. This is the only problematic part in Unit 5. The remaining part are theorems, okay, diagonal language, and universal Turing machine, and then recursive, enumerable recursive. So a lot of theoretical parts are, as well as the theorem parts are available in your Unit 5. Okay, so from this session, so I will start my revision based on the previous university questions. Okay, so I will take some previous questions. Today I will have 4 questions from Unit 1. Okay, so let us have the questions. So I will shift my window. Okay, this is one of the repeated university question, and this is not actually the marks, which is not 13. Actually, this is the uh, partitions mark. Okay, so this was from the A part. Okay, so prove the following by the principle of induction. Okay, so induction means about induction, which is the first unit in the theorem part, proved by induction, proved by deduction. Okay, so a lot of additional and also additional proofs of theorem, a lot of things available in the first part of unit 1. Proof by induction, which is the main theorems, and which is the basis for a basis theorem for all the remaining theorems used in uh, automata theory, theory of computation. Okay, see unit 2 theorems, unit 3 theorems, you will know about the solution, which is in the form of basis as well as induction. Okay, so all the theorems in the unit 2, 3, 4, 5, so followed based principle of induction. Okay, so induction means it follows actually two crises it has, that is basis and induction. Okay, see, this is the solution part. So this is the given problem statement: n plus 1 2 n plus 1 divided by 6. Okay, so prove this by the principle of induction. So first here I will take k in the given. We will have a k equal to 1. Okay. See, what's the meaning of this? This means 1 square plus 2 square plus 3 square up to, okay, n square. Okay, or k square equal to n plus 1, 2n plus 1 divided by 6. So I want to prove this based on the concept basis as well as induction. Okay, proof by induction means there are main two parts. The first part, which is this is the first part, basis. Okay, and this is the second part. Okay, so basis part, which is about a very basic one. Okay, for example, in this theorem, you will take n equal to 1, which is the basic one. Okay, you are applying n equal to 1 means the left hand part, which is 1 square, which is equal to 1, and the right hand part, 6 divided by 6, which is also equal to 1. Okay, so proved. So basis, which is true for both left hand side as well as right hand side. Okay, so basis, which is the step you have to apply for the very basic one. For this n, you are taking n equal to 1, so it is applicable for n equal to 1. So in the induction step, we will prove that it is also applicable for the remaining cases. Okay, so remaining cases, so I will take 1 square plus 2 square plus 3 square up to k square equal, if I will here I will take n equal to k. Okay. N equal to k, so I will apply n in the place of k. So k of k plus 1, 2k plus 1 divided by 6. Okay, this is our based on n equal to k. So this is true as per the given statement. This is true. Okay. So we have framed this equation number 1 based on the given statement which is available in the problem statement. This one. Okay. So we will prove that the statement must be true for n equal to k plus 1. This statement, the previous statement, equation number 1, which is true for n equal to k. If it is true for n equal to k, based on the induction, it will also true for n equal to k plus 1. Okay. So this is the principle of induction. Okay. So in the place of k, I will replace k by k plus 1. So one here, this part will become this. And in the place of k, I will replace k plus 1. This k replaced by k plus 1, so k plus 2. And this k will replace by k plus 1, so 2k plus 3. 3, 2, 2 of k plus 1. Already 1 is there. Okay. So 2k plus 2 plus 3. So 2k plus 3. Okay. This will come like this. So the left hand side, you will elaborately, you will write the left hand side as 1 square plus 2 square plus 3 square up to k square plus k plus 1 square, right? So in the left hand side, okay, see this part, you will substitute equation number 1. Okay, equation number 1. So based on equation number 1, okay, so this part will replaced by k of k plus 1 and 2k plus 1 by 6. Okay, so the remaining part, k plus 1 square here. Okay, so we will take this common as 6. So 6 of k plus 1 whole square. Okay, so some few more steps are added. Okay, finally you will have a basic mathematical steps. Okay, not a new one to you, especially for students, a very basic one. So finally you will have this step k plus 1, then 2k square plus 7k plus 6. Okay, you will write this statement with this one. You can replace this statement with this k plus 2, 2k plus 3. Okay, uh, so thus, okay, see, so this is the k plus 1, k plus 2, 2k plus 3 divided by 6, right? So k plus 1, k plus 2, 2k plus 3 divided by 6. Okay, we have received the same one. Okay, so thus, if the case is true for n plus, if the case is true for n equal to 1, based on the basis, it will also true for n equal to 2. It will true for n equal to k. Based on the induction steps, it will also true for k equal to n equal to k plus 1. Okay, so this is the principle of proof by induction. Okay, this is the important repeated university questions. Sometimes they have made some slight changes over on the given problem statement. Okay. Sometimes n of n plus 1 and n plus 2 divided by 2. The problem statement is varied. Okay, but the principle is same. Okay, so you have to follow these steps. Basis for n equal to 1, then induction. So induction you will take for both cases n equal to k and n equal to k plus 1, n equal to k based on n equal to k. So you will work n equal to, you will prove n equal to k plus 1 is also true. Okay. So this problem statement is over. Next, second one, construct a DFA that accept all strings on 0, 1, okay, except those containing the substring 101. Okay. So in this problem, you are going to construct a DFA, deterministic finite automata. Okay, so the W part, which is sigma belongs to 0 and 1, and the strings actually the construction of DFA, which is based on, which accept all the strings except those containing the substring 101. Except the main thing, except, okay, except those contained in the substring 101. So your DFA definitely can't accept the substring. If any string has substring 101 means definitely it will not go into the final state. Okay, this is the concept. So I will draw for DFA. So DFA, see, so I will take the states beginning with the letter A. Okay, starting state A. See, your automata should accept all the strings except 101. Okay, except 101. First, I will make a transition of 101, 1, no, 1, 0, 3, 1, 0, 1. If any substring, if any string has a substring as 101 means definitely that automata should not accept. Okay, so I don't make this as a C. If it is B means, if it is C, if it is D, okay, I don't make this D as final state. If I will make this D as final state means this substring 101 which is accepted by this automata. Okay, so I don't make D as final state. Instead, I will make the remaining states in the finite automata. All the remaining states in the finite automata will act as a final state except D. Okay, see, this is not a full-fledged DFA. Okay, DFA which has some unique properties like, see, all the states have all the states must have the transitions for both the strings 0 as well as 1, because here your input is, your sigma is 0 comma 1. So all the states should have the transitions on both 0 comma 1. See, from A has was transition on 1 but not on 0. So what about 0? I will make this a self loop. Okay, this is 0. And B has a transition over on 0 but not on 1. So if it is 1 means I will make this. Okay. C, and for C it has a transition on 1, but what about 0 means self loop. Okay. Next, for D, it doesn't have any transition on both 0 comma 1. So, I will make self loop with 0 comma 1, and also, and I'm not saying this is the only one DFA for this problem. Okay, you can draw one or more DFA for the same problem, like that DFA which does not accept the substring 101. Okay, based on my point of view, I will draw this DFA. Okay, sometimes your opinion is different from my opinion. Okay, so anyway, the main goal of the automata, which is that your automata should not accept the substring 101. Okay, this is the main constraint. You have to keep it in your mind. Okay. So I will take a few examples like C substring is 101010. Okay. Here once see, let me check 1010. So 1, okay, I will come B, 0, and move to C, 1, D, 0, D. D is a not final state, yes, because this string has a substring 101. So this automata does not accept for the string 1010. Okay, so this is the right. Then 1110. triple one, 0, 1, 1, then 1, okay, then 0. Okay, it will accept the string triple one zero. It does not have any substring 101. Okay, so then 1 1, then 0 0. Okay, what about this string? So for 1 it will come to B, for another one it will come to A, for 0 it staying on A, another 0 staying on A. A is a final state. This string which is also accepted by this automata. Okay. So one more string 101 if it is means this string has substring of 101, right? So for 1 I will move to B, 0 will move to C, then 1 I will move to D. For remaining 0 as well as 1 I will be in the state B, which is not accepted state. Okay, so almost this automata is the right one. Okay. So this is the way how to draw DFA, deterministic finite automata. So deterministic finite automata has some peculiar properties. So one of the property which is every state has a transition on both the available alphabet. Okay, here your available alphabet which is 0, 1. So all the states should have the transition on both 0, 1 as well as the unique transition. For 0, it will goes into one state. For 1, it will goes into one state. A unique transition for every alphabet. Okay. For 0, if it will goes to one or more states means definitely it is not a DFA. It is a NFA. Okay. This is the property of DFA. Is it clear? Post your chat box. Is it clear? Why B has no self loop? Okay, you will try with B has self loop on 1. Okay, and then only will say this is not is only one solution for this problem. One or more solutions are also possible. Okay, you will draw a separate another automata and post to my WhatsApp, personal WhatsApp. Okay, next you can also make this is also possible. Also possible. Okay. Next, construct a non-deterministic finite automata. So non-deterministic finite automata, which is your NFA. Okay, accepting the set of strings. Actually, this is the 13 mark question. Actually, this question I will take this question, which is from the regulation 2008. 2013 regulation, which is completely different from this current regulation, but 2008 regulation, which is typically equivalent to your current regulation 2008. Okay, uh, so so on this question, this will have the mark 16, but you are having 13, right? Okay, full mark. Say, construct a non-deterministic finite automata accepting the set of strings over A comma B ending in ABA. Okay, so you have to construct a NFA for the string over A comma 0, so ends with ABA. Okay, then use it to construct a DFA accepting the same set of strings. Use it. Okay, why means first you will construct NFA. Okay, then you will convert this NFA to DFA. Which algorithm which is preferable one to convert NFA to DFA? Because this is question, as it is a past B question and it have marks more than 10. Okay, uh, you will apply some algorithm. Algorithm is which is available in your unit 1. That is why I am instructing like this. Okay, Else, you can draw a separate NFA for the same string as well as separate DFA for the same set of string. Okay, which is not also a difficult one, but one algorithm is there in unit 1. What's the name of that algorithm? Can anyone post here? What's the name of that algorithm for the conversion of NFA to DFA? What is the name of the algorithm? Actually, the conversion of NFA to DFA, which is the important part B question in unit 1. Okay, what's the name of the algorithm? Kindly refer your note and tell me the answer if you have your note. Refer your note or refer your textbook and tell me the answer. What is the name of the algorithm for the conversion of NFA to DFA? Actually, this problem, which is the typical NFA to DFA conversion problem. Okay, but here your input is they have given a problem statement as input. That is your first construct NFA based on the problem statement. Sometimes they have given a transition diagram of NFA. Directly they have given the transition diagram of NFA as input. Then based on the algorithm, you will convert NFA to DFA. Sometimes they have given the transition table of NFA as input. Based on the conversion algorithm, you will convert NFA to DFA. But here they have given a problem statement as input. So first you have to construct the transition diagram of NFA based on the problem statement. Yes, finally I have received the answer. Subset construction method. Subset construction algorithm. This is the algorithm. Okay, important one. Sometimes they have given this algorithm as in your theorem part. Okay. Sometimes they have in your university exam they have given equal part for both theorem as well as the problem. Sometimes they have given more importance to theorem, less importance to problem. Anyway, if you are well known about your problem, means definitely you will convert your problem into theorem. Okay, like example, you will take one example. Okay, you will include that problem into your theorem part. Okay, so you will, probably will have a well knowledge in a theorem problem part. Okay, it will definitely helpful you to make your theorems based on the problem. So the name of the algorithm which is subset construction algorithm. We will apply subset construction algorithm to convert NFA to DFA. Okay. First, I will draw NFA. NFA. So I will draw NFA set of all strings over A comma B which ends with ABA. Okay, which ends with ABA. So draw NFA which is very easy one. Compare with DFA. Ends with ABA. A. On receiving first A, it goes to B. On receiving second A, B, it goes to C. On receiving A, B, A. Next A ends with that is ends with set of strings over A comma B ending in ABA. That ends with ABA. Ends with if any string ends with ABA means definitely it will accept. Okay. See, what about the starting? Okay. Definitely your string ends with ABA. The prefix part, whatever it is, I don't care, just AB. Okay, and So DFA has some peculiar property as it has a transition for every input, right? But that is not applicable for NFA. Okay, this is your final NFA. Okay, I won't care about uh, based on the input A, where will we go from the state B for receiving B, the state C. Okay, what about the state C for A and B? So what about the state D? I don't care about these things in NFA. Okay, so this is the NFA for this problem. So any strings ends with ABA, which is accepted by this NFA. I'm going to convert this NFA into DFA based on subset construction method. If you want to apply subset construction method, means first you will have a transition table for NFA. Okay, so you have to write the transition table for NFA, which is the mandatory part in subset construction algorithm. So in the next step, I will write the transition table for NFA. For NFA. So the transition table for NFA, this is AB. And what about the states? Four states, right? A, B, C, D, which is your final state, A, which is your starting state. A on A, it goes to A as well as B. Okay, it goes to A as well as B. So A comma B. A on B, it goes to A only. B on A, no any transition, so 5. B on B, it goes to C. C on A, it goes to D. C on B, there is no any transition, 5. D on A as well as B, both on no any transition, empty. Okay, this is the transition table for NFA. So next, we have B. Next, step number 1, draw transition diagram for NFA. Step number 2, transition table. Step number 3, apply subset construction. Okay. Construction. So directly I will draw transition table of DFA. Okay. After applying a subset construction, based on the subset construction, I will draw transition table for DFA. First, it starts with A, right? Okay. This is the transition table for DFA. See, on A, from the state A, on receiving A, it goes to AB, right? Okay. So that in NFA, this is actually two state, A as well as B. But in DFA, you will make this as a single state, AB. This is a new state. Okay. Actually, in DFA, for a same input, the one or more transition is not applicable in DFA. So I will make A comma B as a new state. Okay, AB. Then this is same A. So one new state is added, right? So new state is added, that is AB. So I will add this new state here. Okay, AB. So AB on A. So AB on A means A on A as well as B on A. So B on A, there is no any transition. So A on A, which is AB, the same. AB means is the same AB. Next, AB on B. So in AB on B means A on B concatenation with B on B. Okay, so A on B, A, B on B, C. So AC, right? So AC, a new state is up here. Okay, so that new state is added in the left hand side, AC. Okay, AC. So A on AC means A on A as well as C on A. A on A on A as well as B, A on A which is A as well as B, then C on A which is D, right? D. When we state is added. What about AC on B? So A on B which is A, C on B, there is no any transition. Okay, so A only. So new state is added which is A, B, D, right? A, B, D, a new state. So ABD on AB. So ABD on A means A on A which is AB. Okay. Next, B on A, no transition, and D on A, there is no transition. So this is AB. Next, ABD on B. So A on B, A, B on B, C, D on B, there is no transition. Okay, so AC only. Okay, so there is no any state which is added here. Okay. No state added is here. See, in this NFA for NFA transition table, the state D has transition on both AB, which is empty state, right? So I will remove this, not necessarily in subset construction. So D is removed, right? D is removed. So consider C. C has a transition on D as well as phi, right? D is removed. So I will also remove C. C is removed. B has a transition on now empty as well as C. C is already removed. So C is removed. This will also make no any change in the transition table. So in the subset construction of DFA table, okay, this is the table for DFA, right? The subset construction of DFA table, we don't add B, C, D. This is the unnecessary steps. Okay, so I will remove these steps. Okay, if you are adding this B, C, D in your subset construction, means this is again this is the unnecessary one. Okay, so you have to remove. Probably you have to remove all these things B, C, D. But in your textbook, they have uh, add all the possible combination steps in the subset construction of DFA. Then at the final state, they have removed the unnecessary parts. Okay, in the subset construction of DFA. But so I will prefer. So you will remove the unnecessary states from the transition table of NFA itself. Okay, don't carry it out in your subset construction. Okay, so B, C, D, these are all the unnecessary states. So I will not consider the computation part in the subset construction. Okay, so uh, so in your transition table of NFA, so what is the starting state? This is A. A is the starting state. What is your final state? This state only has D, right? So D is the final state in NFA. So I will make this ABD, which is the final state. Okay. So I will draw First, the table transition diagram of NFA. So transition diagram of NFA. A which is the starting state, right? A or receiving A on A, it will goes to AB. Okay. A on B in same state. AB on A, same state. AB on B, it will goes to AC state. From AC on A, it will goes to final state ABD. This is your final state ABD. Okay. AC on C, AC on B, it will goes to A. Okay. Then ABD on A, okay, it will goes to AB. ABD on B, it will goes to AC. Okay. See, this is the DFA for set of strings ends with ABA. Ends with ABA. If I will take any string, the ABA means ABA means A, okay, second A, and the third A again AB, and B it will come to AC, next A it will comes to ABD, accepted. For example, B, ABA. So B again A, for next A it will comes to AB, for next B it will comes to AC, next B, next A it will comes to ABD. Okay, so accepted. This is the DFA for ends with ABA. See your DFA, consider all the input alphabet for every transition. See, from A has transition on both A as well as B. AB has transition on both A as well as B. AC has transition on both A as well as B. ABD has a transition on both A as well as B. Okay. This is the transition table of DFA. Just make a note of it. Is it clear? Is it clear or not? Okay. It's an important problem. Subset construction method. What's the purpose of subset construction method? Using subset construction algorithm, you will convert your NFA to DFA. Okay. Next. It is a simple one. Construct NFA with epsilon moves. That is epsilon NFA. Construct NFA with epsilon movements. Epsilon NFA, which accepts a length weights consisting of strings of any number of A's. See, any number of A's followed by any number of B's followed by any number of C's. Okay. Solution. Any number of A's and any number of A's. Epsilon NFA. I will draw epsilon NFA. Transition diagram of epsilon NFA. In your exam, you will add transition table also, if it is part B question. Okay. Any number of A's followed by any number of B's. As this is epsilon, without reading any input, it will move from one state to another state. Any number of B followed by any number of C, right? Without reading in any input, it will move into one state one followed by any number of C. I can also add one more state with epsilon and this is acceptance state, means I will make this C as the acceptance one. Okay, a simple one. This is the epsilon NFA for any strings of any number of A's followed by any number of B's followed by any number of C's. Then so 4 questions we have revised so far. First one, principle of induction, the theorem. Okay, important theorem. Second one, not substring not a part of the automata. Third one, subset construction. Okay, the fourth one, which is how to construct epsilon and alpha. Okay. Is there any doubt? You can ask. So thank you, students.